to the course Advanced Reaction Engineering. So, in this course today we will discuss about the catalysis and catalytic reactors. So, in that we will discuss what is catalyst, catalytic steps, how many steps are there when reactions is there, and say individual steps by considering so many steps are there. So, adsorption, surface reactions and desorptions. So, today we will discuss the adsorptions component and when catalytic reactions are there, and based on that so we will derive the rate law, rate limiting steps, Langmuir isotherms, Langmuir Hinselwood Haugen-Watson type of mechanisms, Ehlers-Danlos type mechanism, Marx von Kalnick type of mechanisms and reactor designs. So, these are the things we will discuss, but today so the things up to adsorptions we will discuss. So far whatever we have studied, so we have studied so many reactions, we have studied catalyst, we have studied many reactors, industrial reactors, that packed bed reactors, CSTRs, plug-for reactors, other different type of reactors we have studied. So, in general the reactions usually we express is going to be this is the reactions usually studied, and these are the different catalysts, means depending upon the material or precursors we take. So, we can prepare a particular catalyst that is required for a particular reaction. The catalyst is specific for a particular reaction. So, means any catalyst, means all these are catalyst, but any catalyst we cannot use for this particular reaction. So, maybe this catalyst effective for this particular reactions, but this catalyst is not effective for this reaction. So, this is also catalyst, but that may be useful for some other reactions. So, this is the reactors. Here we usually put the catalyst in the form of bed, and then from the bottoms we are passing reactants A and B, and from the product we are getting corresponding C and D products if we maintain temperature, pressures, particular flow rates of the reactant. So, by that way we can get the reactions and we can conduct the reactions and we can get the products. So, now what is the catalyst? Catalyst, a substance that we are used for a particular reaction is very small quantity. So, if we do not use any catalyst, so then the reactions may be following this pathway giving product at maybe very low conversions, low selectivity. So, if we use very small quantity of that materials, that may be in the form of metal oxide, metals. So, that if we use, so then it would follow different pathway giving the same products, but different conversions would be different, yield, selectivity would be different. So, that is the use of catalyst, or this is the purpose of catalyst, to change the reactions rate or accelerate the reactions rate. Okay. So, it does not affect the equilibrium of the reactions, but it may change the reactions rate, or it may enhance or promote the reactions by different pathway by following different mechanism of the reactions. Okay, so here you can see the activation energy or energy for a particular reactant. This is the products. So, this is reactions coordinates. So, this is very when there is no catalyst we are using. So, reactions may follow this pathway, and that amount of activation and energy is required. So, we can get this product. If you use catalyst, then its reactions may follow this pathway, we are getting this product. Another catalyst we can use, so they are also following different pathway. Another catalyst we use, this catalyst one. So, here activation energy is this. So, here activation energy is this, and here the activation energy is this. So, this way means the catalyst, if we use the activation energy, maybe E activation energy, that is without catalyst, E activation by using catalyst once is less or lower than that. So, that way catalyst help to down the reaction temperature, lower the activation energy, that way it help to easy the means conversion for reactant to product. Okay. So, in the gas and fluid systems, gas is the reactant and solid is the catalyst. So, in that case catalyst usually we express in this is our reactor system. Here catalyst usually considered in a spherical forms or cylindrical forms, or maybe some different forms we can design that catalyst, we can give a particular shape of the catalyst, that we will discuss later. So, once that catalyst is there, let us say nickel alumina catalyst is there. So, nickel may be in the +2 oxidation state, means nickel oxide in the form of this, may be in this catalyst, or maybe nickel 0 oxidation state, means purely metals, small metal is there, or maybe nickel oxide. So, depending upon the nature of the reactions is required. So, either it is this forms or this forms. So, either way we can convert that as per requirements. So, this is nickel alumina catalyst. So, here red component that you can see, this is the nickel metals, and bottom one, that is the blue one, that is the support alumina. So, this support usually material is inert materials, does not take part in the reactions, but it would provide high surface area, whereas the active component is this metals. We can distribute uniformly as this way that it can come in contact with the surface, and reactants will be may get adsorbed over there, may convert it into corresponding products. That way may means helps. So, whenever talk about the catalyst, it is form of the spherical forms. I said in the catalyst there are so many pores are available. The pores, this is called pores. The pores may be means different type of pores are available. So, here you can see this is the pores we can say. So, this is the pores, it is called maybe a large diameter of the pores. So, here this is the active sites that is distributed here, here. So, here this is the pores, here reactant molecules will come and may follow these pores to go inside of that catalyst pores through diffusion that already have discussed, and then it may interact with the active sites and may convert it into the corresponding product. So, here the pores are available, this is also pore, this is also pore, this is also pores. So, different type of pores are available, so that is depending upon the diameter of the pores. If the pore diameter is very small, in the less than 2 nanometer, so then it is called micropores, and if it is 2 to 50 nanometer in that range, so it is called mesopores, and if it is more than that, so then it is called macropores are available inside of that catalyst or catalyst surface or inside of the catalyst. Okay. So, depending upon the nature of materials, pores different, means one catalyst to another catalyst, may depending upon the method of synthesis. So, method of impregnations of that active metals inside of the catalyst. So, the pores distributions also would be different depending of thermal effect when we are preparing a catalyst. Depending upon that, different type of pores formations are there, and all the pores are nanopores, or we can say this is the porous materials or nanoporous materials we can say. Okay. So, here depending upon that, the here in this particular silica alumina support, here the surface area it is very high, 300 meter square per gram catalyst, pore volume is usually 0.6 centimeter cube per gram, and pore radius 4 nanometer. So, 4 nanometer it is coming mesopore range 4 nanometer. So, then these materials we can say it is a mesoporous materials. Okay, depending upon experimentally these are the things we can measure, and based on that we can say whether the catalyst or the surface we have used, that is mesoporous or microporous or macroporous materials that we have synthesized. Okay. So, sometimes pores are so small, what is the use of these pores? So, sometimes the pores are very small, so then it would pass small molecules. So, these pores is, if it is suppose we have a molecules reactants, another molecule is reactant, these are the reactants, this is A and this is B. When it is passing through this catalyst or reactors, so then through here A will pass, but B will not pass. So, it would be, since the pores is very small, so B particles or molecules cannot pass through these pores, only A molecules may pass and can slip from this catalyst pores. So, therefore, so when if we conduct any reactions, so then or if you want to get separations using this type of materials, so then that would help. So, one molecules, suppose these are the two molecules are present in a mixtures in the form of gas. If you want to separate out A from the B, that way you can do. So, these are the materials we can use. Okay. These are the porous materials, sometimes it is called molecular sieves also, it is zeolites also, or certain kind of clay, aluminosilicates type of compounds you can say. So, here the pores ring, it is shown here 7.4 angstrom. So, depending upon the materials we are synthesizing, the pore structures, pore formation should be different, pore radius, pore dimension should be different. So, if we follow the same method of preparations, but if we change one or two parameters for that particular preparation, so then property of the material should be different. Okay. Now, we need to discuss about the absorptions, that is physiabsorptions or chemiabsorptions. So, whenever we talk about the catalyst and any reactions, so here this is our catalyst, this is our reactants. Okay. When reactants come in contact with the surface of the catalyst, we are not doing any reactions, just catalyst we have taken reactant molecules just at maintaining same temperature inside of this containers or reactors. We have just put catalyst and molecules A and A that we have placed here. So, here what would happen? So, it may physically absorb over the surface of the catalyst this. So, just come in contact and due to the van der Waals force of attractions they may get attached with the surface of the catalyst, but there is no bond formations. So, that physiabsorption process may be exothermic, small amount of heat may be released during this process. So, it may attach like this way or maybe it may attach this way, means molecules may dissociate and make some bond with that catalyst, and maybe that way dissociative adsorptions or this way chemiabsorptions, chemical bond formation is there. So, the bond may be covalent ionic or metallic bonds, and the process is also exothermic, but here heat of adsorption is little bit higher than as compared to the physiabsorptions. Here small amount of the heat release would be there, here high or large amount of the heat would be released. So, these are the basic difference in between these two. So, either this way absorptions may be there or this way may be adsorptions be there. So, physiabsorptions usually if we notice this, so this is the distance between molecules and the surface of the catalyst, and y axis that is the energy, this is negative energy, means if physiabsorption is there. So, dph that is the distance, means catalyst surface, this is actually this catalyst surface and the molecules that is the separations, and this is the distance. So, here the distance is Morse, this is the distance is Morse, let us say this for chemiabsorptions. Here the energy is required or release, amount of energy release for this absorption should be high as compared to this. Here physiabsorption requires low energy and chemiabsorption requires or release or evolve. This is the exothermic process, heat would be evolved or released from the system, so that would be very high. So, its value may be in this range or maybe some other ranges also there. So, depending upon that the systems we are discussing or talking. So, chemiabsorptions, physiabsorptions we have discussed with that. So, this chemiabsorptions or physiabsorptions, what is the things happens over the surface of the catalyst, the active sites over which the reactions occurs. So, here you can see this is the support and this is the active sites. This is support materials or SiO2 here Al2O3, this supports is active sites is nickels. So, here this way means things are happened. So, active sites over which the reactions occurs stabilize the intermediates or chemical species for the reactions, and this stabilizations of the intermediate is the key in the design of any catalyst. Means whenever a reaction is proceeding over the surface of the catalyst, reactant may come into the surface of the catalyst, get adsorbed, and then it forms some stabilized intermediate species or chemical species that part converted into the desired products, or maybe some other undesired product, maybe any product formation should be there or conversion should be there that way. So, this is the the things we should know, and with that turnover frequency also sometimes we need to express the rate of the reactions. Means we have taken one active sites, let us say, and we are passing reactant molecules through that. So, here if we know per gram of the catalyst how many numbers of active sites are present, so means 1 gram of catalyst, so how many number of active sites, that experimentally we can measure and we can evaluate that. So, a number of active sites are present. So, through the 1 active sites per second, 1 second how many number of active sites come in contact and converted into the product. So, that if we are able to evaluate means per active sites roles of per active sites for transformations from one reactant number of reactants molecules per second. So, then the turnover frequency we can say or we can express that the quantify the activity of the catalyst, the number of molecules reacting per active sites per second during reaction. So, turnover frequency usually expressed in terms of the number of molecules reacting per active sites per second during the reactions. Okay. So, therefore, the dispersions of active sites means if we prepared a catalyst this way means dispersing more and more number of sites, and here another catalyst we have prepared 2 active sites are there, here number of active sites are more. So, more of sites are available means here dispersion is less, here dispersion is more means active sites dispersion. So, dispersion of active sites of the catalyst is very important when we are going to synthesize a catalyst. Okay. So, that part is very important. So, okay, this is that this way you can express the turnover frequency number of molecules A converted per number of active sites present per unit weight of the catalyst and per seconds. Okay. Now, the steps in the catalytic reactions. So, that is very important that we are going to discuss. So, let us say a catalyst we have, through that we are passing the reactant molecules. So, then once the reactant molecule is passing through the catalyst surface, it get adsorbs and then it converted into chemical reactions would be theirs, and then it converted into the corresponding products. Then the products come out from the surface inside of the reactor catalyst to the outside of the catalyst, and then it would come to the outsides, and then from the reactors to exit and we can get the products. So, here the steps are given steps 1, steps 2, step 3, step 4, step 5, step 6 and step 7, 7 steps that is discussed here and given here means the one by one means what is happen with the reactant molecules to this is the reactant molecules A reactants, it is converted into B. So, in presence of catalyst inside of the reactor, so what is happened first reactant A is entered, that is the external means bulk phase is there. So, in the bulk stage. So, from here to the catalyst surface it would be diffuse means if there is some concentration differences are there. So, external diffusion is there, through that molecules enters to theirs, and then external diffusion is that means from bulk to the catalyst surface. Once it reaches to the catalyst surface, diffusion of reactants from the pore mouth to the catalyst pores. So, this is the catalyst pores, here you can see catalyst pore is there. So, inside of the pore mouth is there. So, here reactants reach from here to here by step 1. So, once it is reached here, then this is called external diffusion, and then it is reached to the here through the pores it would moves. So, this is called internal diffusion. Second step is the internal diffusions. Okay. Once it is reached there, then adsorptions would be there. So, adsorptions means reactant molecules come in over there, and this is the surface of the catalyst, here it get adsorbs. So, then third step is the adsorptions. Once it gets adsorbs, so then it would be converted into corresponding product. A would be converted into the products. So, inside of the catalyst once it is reached, once it is get adsorbed over the surface, it does not remain as A, it would be converted into B. These reactions would take place here over the sites, active sites. So, then from here we are getting B, not A. From here up to A we are getting A. Okay. So, from here after converting A into B, we are getting product B. So, pore diffusion should be through these pores, again it would be B component would be diffuse through these pores, it would reach here. So, internal diffusions of the component B. So, then means desorptions would be there. So, from here it would be dissolved, and once it is dissolved, so then internal diffusion, this is the pore diffusions. So, from here desorptions, and after that internal diffusions of component B, the B would be diffuse. So, then from the outside of the pores it would be come to the bulk. Okay. So, external diffusions is there. These are the 7 steps is given here. So, these are the way, means we can say that the reaction reactant to product formations by formations of for following various steps. So, 1 to 7 that is discussed here. So, most of the cases, means whenever we will discuss by considering these are the 3 steps very important, 3, 4, 5. So, point 1, 2 and 6, 7 both are the same. 1, 2 is the external diffusions, then internal diffusions and for reactants, and this is for product 6 and 7, and so 1 and 2 for reactants. So, this is internal diffusion, external diffusions. So, if we do not consider those things, so then step 3, 4 and 5 that we have to consider, that is for adsorptions of the reactants over the surface of the catalyst, then surface reactions, and then desorptions of the product from the surface to the surface, from the surface. So, these are the 3 steps are very crucial, and one by one we will discuss. Okay. So, step 1, that is the diffusions. Means whenever we are going to discuss about adsorptions, so reactants onto the surface of the catalyst, before that we need to discuss about the bulk to the external surface, the catalyst diffusion, that is very important. So, here that depends on that flow rate of the reactants that is passing through the bed of the catalyst or surface of the catalyst. So, in that case, if velocity of the fluids that is are very low and very high, depending upon that some boundary layer formation, this is the thick boundary layer formations is there. So, if the flow is low, then thick boundary layer formations would be there over the surface of the catalyst, outer surface of the catalyst, and when velocity is very high, so then thin boundary layer formations would be there. This is the thin boundary layer formations outer surface. So, it has some specific dimensions or distance of the thickness. So, we can express in terms of delta, that is the boundary layer thickness. So, that we have studied in heat transfer. So, boundary layer thickness or boundary layer theory. So, fluid dynamics also we have studied that. So, here's rate usually expressed in terms of Kc, bulk concentration of the component A, and CAS, surface concentrations. If there is differences is there, so then rate would be like this way, and Kc, that is the mass transfer coefficient, we can express in terms of dAB by delta. dAB is the diffusivity, okay, diffusivity of the systems, equimolar counter diffusions you can say. So, and delta is the film thickness. So, if you know dAB delta, then you can put Kc value, and if you know the bulk concentration, surface concentration, we can find out the rate. So, if we actually this Kc value mass transfer coefficient as a depends on the fluid velocity and particle diameters. So, fluid velocity and particle diameters if you know, and if you vary that, then so overall rates this way it would vary. So, from here to here, so external diffusion is the slowest steps, and here external mass transfer no longer the slowest steps here. So, up to this means this particular velocity or flow or particle diameters, it is changes exponentially or parabolic nature is there, after that it remain constant. Okay. So, if we eliminate that component, so that way we have to adjust that velocity or fluid flow. So, next is the internal diffusions. Internal diffusions is also very important, means we know this is the surface concentration Cas, and inside of that port the concentration of the reactants is Ca. So, Ca that is the surface concentration of the reactants when diffusion is there through internal diffusion, through pore diffusion. So, reactants will enter inside of the pores. So, that rate directly proportional to the Kr into Cas. So, Crs is the surface concentration. So, surface concentration is more, so rate would be more. Okay. Now, we are coming to the adsorptions. Okay. Adsorptions means this is the first steps I said. So, means there are 3 steps: adsorptions, surface reactions and desorptions. Means these are the 3 components we will discuss. Out of that, only adsorptions we are going to discuss, means how reactant molecules when come in contact to the surface of the catalyst, how they get adsorbed, and what are the natures of that adsorptions isotherms if we increase the pressures of that reactants, means at lower pressure to the higher pressure. So, then what would happens in adsorptions, and if the adsorptions is dissociative, non-dissociative. So, that are the things we will discuss. Okay. So, let us say A and B both are the reactants. So, that is get adsorbed over the surface of the catalyst. So, A and B may get adsorbed. See, these are the catalyst surface, these are the active sites. So, in the active, these are the back end active sites, and this is the sites where A and B get adsorbed. Okay. So, these are the sites, occupied sites, this is unoccupied sites. Okay. So, a particular catalyst, whenever we design a catalyst, so these active sites are fixed. So, this is called total active sites, CT. CT is the called total active sites, and if A molecules adsorbed here, so then CT equals to actually 4 here, let us say. So, here CB vacant sites equals to 4 minus 1. So, vacant site is 3. So, CB this is 1, 2 and 3 vacant sites are there, total sites are 4. So, if another molecules get adsorbed, so then vacant site is this. Okay, this way you can express. Okay. So, this is vacant site, total sites of the catalyst surface sites are available. So, here let us say A molecules get adsorbed sites 1, this is sites 1, this is sites. So, sites 1 where A molecules get adsorbed, it forms AS. Similarly, for another sites are available, so where component B that get adsorbed, it forms adsorbs BS. So, A gets adsorbed, B gets adsorbed. So, it actually indicate this, it indicate actually this. Okay. So, means not this, this and this. Okay. This is in the gas phase, means these reactions actually indicate. So, this is the final. So, total concentration of the surface sites that we can write this way, CT equals to total sites, these 4 equals to CT equals to vacant sites 1 and 2, CB vacant sites plus adsorbed sites by A, adsorbed sites by B. So, this is the total sites. If it is 1 1, so CB the vacant sites 2 plus 1 plus 1, like this way it is coming. Okay. So, total sites, number of sites available, vacant sites available, the surface sites where A gets adsorbed, surface sites where B gets adsorbed. So, this way you can express the total number of sites. Next is the molecular adsorptions or these adsorptions of the component A. Let us say we have taken CO, carbon monoxide molecules, and we have the surface sites catalyst here. Okay. So, here surface sites are available, CO gets adsorbed. So, CO gets adsorbed directly if it occupy or interact with one side. So, the adsorptions would be like this. Okay. Adsorptions would be like this. So, if 2 sites surface sites CO gets adsorbed, so then we can write this CO interacted like this, and it may be this way, means dissociate, this is called adsorptions. Non-dissociative adsorption, this is dissociative adsorptions. Okay. Dissociative adsorption, this is molecular adsorption or non-dissociative adsorptions we can say. Okay. So, this way it can be. Okay. So, either this way or this way, means by considering non-dissociative adsorptions or maybe dissociative adsorption, means CO dissociate into 2 components and it is occupied into 2 different sites of that catalyst, it is available C and O. This way it may get adsorbed. So, this is dissociative, this is non-dissociative adsorptions. Okay. So, now this dissociative and non-dissociative adsorptions how it is. So, that part is we have discussed. So, now in our next class, so means details after these adsorptions means different isotherms how it is. So, that part we will discuss. Okay. So, it means for dissociative adsorptions, non-dissociative adsorptions, how to derive the isotherms or other parameters. So, that we will discuss. Okay. So, today is up to this. Okay. Means just adsorptions we have started. So, rest of the things we will discuss. So, many things are there. So, it is not possible to discuss everything. So, today is up to this. Okay. Thank you.